how many folks know what a cover 2 defense is? Oh, wow. That's a lot more than I thought.
All right.
How many folks know how self-attention works in transformer models? Okay.
All
So
right,
half and half. Yeah. That's great. I think we're going to be talking about both of those things at the same time today. We're going to be specifically talking about how we develop custom transformer models for the NFL for decoding defensive coverage schemes. So before we start, I just wanted to highlight the core members of the team. Mike, who's here, Amy and Keegan are from the NFL side. And Chris, myself, and Ornab and Evan, we're from AWS. And here's the speaker team, but without the whole team, this project would not have been possible. So, as for the agenda today, Keegan's gonna kick us off with some quick introduction about the NGS program and how the NGS platform has evolved over time with the partnership with AWS. And then we'll dive into the focus of this year's project, which was coverage responsibility. And then we'll talk about the solution we developed and the results, and we'll leave some time for Q&A. So if you have any football questions, we can answer them. All right.
Great. So Next-Gen Stats is the NFL's live tracking data operation. I'm sure many of you in here might be familiar at this point. If you've watched an NFL game in the past year, you've likely seen one of our packages or our graphics. But to take it back for those of you who are unfamiliar, every player is wearing 2 chips in their shoulder pads, and we get their locations 10 times per second, which creates this really robust tracking data set that we then use to generate over 500 stats in near real time. Our team specifically supports all the broadcasts. We have an analyst assigned to every broadcast crew on every single game, providing real-time analysis over Slack and headset, as well as putting together pre-game research for all of these broadcast crews. Additionally, this is leveraged across our NFL ecosystem. So all of our clubs have access to this data, which they use for personnel, for scouting, for coaching, for sports science, as well as the league office in New York, who uses this for player health and safety, as you can see over there on the wall, and the rules committee. But enough about me. I'll let Tom Brady and Kevin Burkhardt kind of give you a preview of what this looks like in action.
Here are today's Next-Gen Stats powered by AWS, and it's Mahomes facing a Vic Fangio blitz, something he never did in the Super Bowl.
We did not think we'd talk about blitzing in the Eagles defense. 7 blitzes, that's more than the Chiefs offense probably worked on in practice the entire week. This one is pretty simple, just off his right side. No one to pick up Makuba there. You're dealing with Jalen Carter and this Nolan Smith and this pass rush. They've decided we want to man these guys up a little bit without Rashee Rice, without Xavier Worthy. Can these guys get open? They haven't really proven they can.
Here's the check, though.
So let's take a step back and look at the evolution of Next-Gen Stats. We've been around collecting data for in our 10th season now. And going back to 2016, it was very simple. It was logic-based stats. It was, how much distance did a player travel? What was their top speed on a play? Where were they aligned? Where did the quarterback throw the ball, etc. Starting in 2018, we partnered with AWS to build new machine learning stats every offseason. And that was really the inflection point of our stat development timeline. As the official cloud AI and ML provider of Next-Gen Stats, AWS has truly unlocked our potential. While we started with that partnership with more complex models to quantify traditional stats, like what were the chances of a completion, or how many rushing yards we expect this running back to gain at handoff. Over the last couple of seasons, we shifted our focus to classifying real football concepts. This way, we can meet our broadcast talent where they were and speak in their language, making them more comfortable and make it easier for them to buy in to the value of NGS. So that brings us to coverage responsibilities. So what do we mean by that? Well, in the before times, aka last year, we could only tell you who lined up against who and who the nearest defender was by distance to the receiver when the pass arrived. We thought we could do a lot better, and that's when we turned it over to this crew right here for our off-season project. So we split this problem into 3 pieces. 1, what is every defender's assignment on a given play? 2, who is covering who? And 3, finally, tie it all together, who's responsible for the targeted receiver on a given play? From this, we can derive tons of valuable insights that we'll get into later. But I'll kick it back to Kevin first to talk about how the sausage is made.
All right. Okay, so now we'll kind of dive into the solution we developed. If you look at this play on the left, you see a bunch of players moving left, right, top, bottom. It might look like it's kind of random, but behind every player's movement, there's intention. So there's a game plan that the coaching staff gave them. The players are reacting to how the play is evolving over the play. And they're reacting to opponents, but also their teammates. And so the question that kind of came back to us was, how do we develop a model that fits this exact problem? So we did a little bit of literature research. We found this model architecture, factorized attention. It suits well for this problem. It's been implemented in self-driving cars. So in self-driving cars, you have cameras and LiDARs that are detecting a bunch of different objects, people, and it's trying to make a driving decision. But in our case, we have a bunch of players moving around the field, and we're trying to make a prediction about what the play is, what the players are trying to do. And then this architecture basically serves as the foundation for the 3 models that we developed. They're also very lightweight. Roughly, we had about 700K parameters. Compared to the billions in the LLMs that it's out there, it's pretty small. But yeah, this is a shared architecture among the 3 models that we'll be talking about later today. All right, so I just wanted to kind of give you a high-level overview of what factorized attention is doing. So if you have a full attention, you're basically trying to make connections between all the input features. That not only increases your computation costs, but you can imagine you could diffuse your attention across many different things that are not necessary. And so what factorized attention does is you kind of streamline your attention along the dimensions that you actually care about. And so in our case, that's time and space. And this also decreases the computational costs, but also it kind of lets the model learn what we want them to learn. And so the analogy that I like to use is using a full attention is like trying to solve a math problem while riding a unicycle and juggling. And then factorized attention is basically just trying to do one task at a time. And just wanted to make a quick comparison to large language models. They're all transformer-based. And so in LLMs, you can input short or long sequence, but it will still make a prediction about it. And so in our example, we have the short sequence and the long sequence, but you might be able to infer that it might be coming from a Chiefs fan. And we wanted to take that same architecture and use it to our models. And so even if you put in a short sequence of play or a long sequence of play, you can still make accurate predictions. All right, so in terms of the training data that we had about 5 years worth of data collected. And so this goes from seasons 2020 through 2024. And this amounted to about tens of thousands of passing plays total. And in terms of the 4 main categories of data sets, we have trajectory, events, player information, and the coverage responsibility labels. The trajectory data, we have, Keegan talked about it. It started with the XY coordinates, but we actually also calculate other derivative metrics, so speed, acceleration, orientation, and direction, and all of those get fed into our model. And then we use events data. This is very useful for kind of cleaning up the plays, because you have information about when the ball was snapped, when the pass was thrown, when it was caught. And then you have player information data set, which tells you who's who and what team they belonged to. And lastly, the most important data set is the human annotated labels. The coverage responsibility labels, it has 19 different class of individual coverage assignments. It tells you who's matched up against who and who was a targeted defender in that play. And I think Keegan can talk about it more, but if a human was to do this for a single game, annotating, I think Keegan mentioned that it would take him 8 to 10 hours or so to go through a single game. But now we can do this in sub-seconds. All right, and then here are some details about the data processing we did. First, we filtered only valid plays. And so in this set of problem, we only care about pass plays. And so we only select pass plays only. And then we select for plays with human annotations only. And then when we clean up the plays, we only grab 3 seconds prior to snap all the way to pass caught. And this allows us to kind of throw out the unnecessary data that's not relevant to the play itself. And then we apply normalization. And so, as you can imagine, football games go from right to left and left to right, depending on who has the ball. But we want the model to learn to predict as a same play that's going right to left versus left to right, make the same prediction. And so we normalize everything to the same direction, going in a positive direction. And then with that, we also have to normalize the player orientation, because when you flip them, their orientation also changes. And then lastly, we introduced this data augmentation scheme. So when we train the model, we will truncate the plays, the cleaned up plays, to go from any frame between -30 and snap, all the way to snap to pass arrival. And this kind of augmentation actually allowed the model to be more robust to the length of the play. All right.
Thanks, Kevin. So, getting into our solution, the first thing we set out to do was classify each player's assignment on a play. Let's go back to the playbook a little bit. Can anyone here name what this coverage is? Well, that's cheating. Thanks, Mike. As you can see on here, each player is a zone coverage. Each player is responsible for a specific area of the field, and they will generally take a receiver if they enter their zone and pass them off if they leave their zone as the routes develop during a drop back. Let's take a look at a real play here. So, Giants are lined in a 3-by-1 formation. The Buccaneers have a single high safety on the top, and in typical Todd Bowles fashion, since it's 3rd and long, they'll stack the line of scrimmage, trying to manipulate the protections with their front 7. Most observers from the sideline, the quarterback, will see this and think it's going to be cover 1 or cover 3, a single high safety patrolling the middle of the field, and these guys underneath either playing man coverage or zone coverage. However, right as the ball is about to snap, we can see that top corner up there backpedaling and this bottom corner rotating into the flat. it actually plays out as cover 2. Now, let's go beyond just the film and get back into the data, and I'll hand it off to Chris for that.
Yeah, so let's take a look at what the model's actually doing for us here. So we've already established that we can classify coverage at the play level, but our coverage assignment model goes beyond that. Now what we're doing is we're classifying one of 20 coverage assignments for each of our 11 defenders active during the play. Looking at this visual, we're only looking at the pre-snap results of the model. We've colored our offensive players in yellow, our defensive players in red, and we've also indicated what the ground truth label is as well as the model's prediction. I guess at this point, since we're talking pre-snap, you might be wondering, how is it that you can make predictions with just pre-snap data? You don't even know, the players haven't actually started moving throughout the play. But reflecting back on what Kevin was saying about how we prepared our data, the data was prepared in a way that the model is used to seeing data of varying lengths, windows of varying lengths. So it's used to seeing data that's just pre-snap data. It's used to seeing data that overlaps, maybe 3 seconds prior to ball snap, as well as all the way out to the pass arrival. So just with pre-snap data alone, the model's able to make predictions. Now, it's not perfect. In this example, you can see that it did successfully make one prediction correct. The edge rusher is playing hook curl right, just as the label, just as the ground truth label indicates. If we were to compare this to large language models, this would be kind of like a large language model predicting what the object of a sentence is given only the subject without a verb. Now, at what point does the model have enough context that it can make better predictions? Next, we'll go ahead and take a look at the results just at once the model has full context, so at pass arrival. Here you can see that all of our predictions were correct. So the model's successfully able to identify the coverage assignments that every defender is playing. And so if we take a step back and again compare it to LLMs, this would be kind of like how LLMs can accurately predict the object of a sentence once both the subject and the verb are provided. So at what point did the model have enough context that it was able to make these predictions correctly? Here you can see on the left an animation of the same play that we just looked at from beginning to end with the predictions made frame by frame. On the right, you can see the change in prediction accuracy as the model has more context and more data against which it can infer. And you can see that as time progresses and we hit that ball snap event, our accuracy shoots up from 17% to 100%, only 400 milliseconds after ball snap. And we can also identify some pretty interesting events, such as the cornerback at the top of the play rotating from deep third to deep half right, only 200 milliseconds after the ball snap occurs.
And this is really doing what the human eye is doing. And shout out to Todd Bowles for a very well-timed disguise here. The fact that the model and the human eye probably isn't picking this up until right after the snap shows the great coaching and having all of his players on a string in this example. So why does a coach disguise a coverage? Well, it's to confuse a quarterback, but why do coaches not often disguise coverages is another great question, and it's because it leaves yourself vulnerable to a lot of mistakes. Your cornerbacks will have to cover more ground. There could be missed timing. You could give away the bluff before the play, and then the quarterback can take advantage of that hole in the zone that you've left because you've forced your corner to cover so much more ground. So now we can accurately take a look at what defenses actually do this the most. So how often are defenses playing their cornerbacks as the deep half player? Traditionally, too high shell, you'll have both safeties rotate back, but there are some coaches that like to mix up the pre and post snap picture. The madman Brian Flores is the purple dot you see all the way over there, the defensive coordinator of the Minnesota Vikings, as well as Chris Shula, who I'm sure will be getting a lot of head coaching interviews as the defensive coordinator of the Rams this year, coaching one of the best defenses in the league. And this also shows you the diversity in play calls from a defensive perspective. All the way on the right, there's a missing bar because there is a defense that hasn't done this once all season. And that's the reigning Super Bowl champions, the Philadelphia Eagles, under defensive coordinator Vic Fangio. So now that we have everyone's assignments, it's time to get to the game within the game, the one-on-one matchups, the fun part, who is guarding who. And this is like catnip for broadcasts. This is where we're seeing the most instant impact in terms of our ability to tell stories in real time. This screenshot right here is from a Week 10 game on CBS with the Tony Romo and Jim Nantz crew. They came into the game really wanting to highlight this matchup. We're able to provide that real context live, and it looked like Christian Gonzalez, the second-year lockdown corner, really was winning that matchup against the rookie sensation Emeka Egbuka, holding him to just 2 receptions on 7 targets. So once again, Chris, go ahead and take us through the data.
Yeah, so defender-receiver matchups, this is a very exciting metric. So what is the model really doing? Well, ultimately, it's just trying to identify who's guarding who. And here's another visual breakdown of what a play might look like and the model making its predictions of which defender is matched up with which receiver at pre-snap. You can see that we've drawn these solid lines to indicate whether the prediction was made correctly or incorrectly, and we've also provided probabilities here as well. You also see some dotted lines present. You can ignore these. These are basically the future trajectories that the players would follow, but the model doesn't have access to that data yet at this point in time. We're using the same truncation strategy for player matchups as we did for coverage assignment. So the model is effective at making predictions pre and post snap. And it's quite robust, actually. In many cases, we see that the model is temporally robust. It has about a 75% average prediction accuracy when just using pre-snap data. And the model can identify coverage intentions pretty early in the play and then track how those matchup assignments evolve as players' routes develop over time. If we take a look at the pass arrival predictions, so predictions made once a full contextual window is available to the model, we see some changes to the matchups that had been predicted. Generally, we see about an 89% accuracy in model performance once we have full context. Ultimately, the model is capable of confirming matchup assignments as plays unfold. It's not perfect. You can see in this case that there are some mismatches still, but that's not a bad thing. And the reason for that is that these are pretty complex scenarios that we're having to make predictions against. Defenders react as receivers and their defensive teammates change their direction. And sometimes there are even incorrect labels in the training set.
So as we can see here through the GIF, because it's a temporal nature and we're comparing to play-level tags, there might be a little bit of mismatch here, and it's not necessarily a bad thing to have a missed assignment here. So as we can see, by the end of the play, that cornerback that started as matched up with that tight end that's breaking inside, we're counting that as a miss, but the cornerback went to his zone, the curl flat zone in a cover 3 scheme, whereas the tight end breaks inside. In the end, it's really just a well-designed play by the offense because you see the tight end and that wide receiver are kind of high-lowing that inside linebacker that's responsible for the curl hook zone right there. So even when we're saying it's a miss, we're kind of comparing apples to oranges in terms of the accuracy here because we're taking play-level labels once again and getting temporal, much more valuable labels for every 10th of a second. And now that we have matchups for every play, we can really get to some cool evaluations of these cornerbacks. So we know how tight they could be playing in coverage. What's the difficulty of their matchups overall? So if we're looking on the next screen, we can tell you now which cornerbacks play the stickiest coverage. So as a defensive back coach would say, sticking in their back pocket throughout a play. And we can see right here, Sauce Gardner, number 2, who just was traded to the Indianapolis Colts for 2 first-round picks. Shows you how much they value him. He's spending almost 2/3 of a second per matchup in tight coverage, which we've defined as with staying within a yard of your matchup on a given play. Finally, let's tie it all together with the target defender. This is, in the end, the simplest stat to tell. What do you give up in coverage? And we need to know who to credit with each pass attempt. As we said before, we used to do this by proxy by just taking the nearest defender to the targeted receiver when the pass arrives. But that's not always the case. We said 75% accuracy, so 25% of the time we were misclassifying that. And as you can see here, there's two defenders right around Isaiah Likely in the back of the end zone here. Who's actually responsible for allowing that target into the back of the end zone? Well, that's what this model does. It's a much more robust way of seeing how the play develops. So maybe a safety that's coming down to help his cornerback that ends up being the closest to the defender isn't getting debited when that receiver catches the ball and we say he gave up 40 yards in coverage. It really just overall levels up and makes ours more accurate in terms of telling the story about cornerbacks and all coverage defenders. And beyond that, what we can do now, traditionally you think about cornerbacks, you think about Darrelle Revis, Hall of Famer. He made a whole brand about Revis Island erasing opposing receivers. A cornerback's job is to not be targeted at all. So now that we have targets, matchups, and assignments, we can put that together holistically to tell a much greater story about every defenders in coverage and on the 80% of snaps that they're not being targeted. So let's look at this next graph right here. Again, a cornerback's job is to not be targeted at all. So traditionally, target rate is a good way to say, hey, this guy is deterring targets. But what if you're asked to follow a opposing number one receiver across the field all the time? We had no way of showing the difficulty of each matchup before, but now we can. We can see Sauce Gardner with that great tight coverage metric also is above average in terms of target rate allowed while facing the opposing team's leading receiver on nearly 50% of his matchups, which is a huge outlier in terms of the difficulty of what he's being asked to do on a play-by-play basis. And now let's get into the outcome and business impact. I'll kick it back over to Chris.
Yeah, so these models are quite performant. Altogether, the three models do generally achieve greater than 88% accuracy. However, when we reevaluate the model's performance against a sample of 100 plays, we actually found that 5 to 10% of the data was mislabeled. That means that when accounting for human error, our models are actually achieving prediction accuracies of about 95%. That means ultimately that we're outperforming human levels of accuracy. Not only are these models accurate, they're also fast. We're able to make inference in about a couple hundred milliseconds. When you also account for some of the data pre-processing in real time, these new stats are generated with sub-second latency. And as I recall, that's quite a bit faster than manual methods, right?
Yeah, so I started my career as a data charter, and we would collect maybe 50 given data points on a given play. And that would take us about 8 hours to get through one game. And we're not even collecting who's matched up with who on every single play, how that evolves over the course of a play. So not only is it more, it's way faster and we can provide it to broadcast in real time without having to pay an army of data charters, but it's also just way deeper insights that we're able to tell, better storylines. As I've shown you before in those couple of graphics, we're really just scratching the surface in terms of how defenders can, perform their jobs well and perform their assignments as they're asked. And the proof is in the pudding here. So we've seen a 350% increase in year-over-year broadcast integrations when it comes to individual coverage performance. And when we launched it in week 4, I'll once again show you Tom Brady, Kevin Burkhardt,
Take a look at Quinion
show you how this
Mitchell
looks in real time.
Sensational.
Yeah, just all you can ask for is a young player to be around the ball, and he's got a lot of length. So whenever he's close, he's got long arms, he's got a good reach, and he's got a great feel for when the ball's in the air. See, just...
So that one highlighted budding star Quinion Mitchell, who, if Myles Garrett didn't exist, might be a leader for the Defensive Player of the Year race this year. This was one of his great games, but overall in the season, I can tell you that he's allowed about a 43% completion percentage in coverage, which is by far the best we've seen in a season in our database. It's really cool to be able to tell these stories in a much more robust way. And once again, shout out to the AWS team for helping us make this dream a reality. Kevin, here you go.
All right. I just wanted to share a few more resources. One thing that I do want to highlight is the AWS Sports website. This has information about all the partnership between AWS, NBA, NFL, F1. So you can check out that website. And then there's some other blog posts that are really interesting. I think personally, the 2025 top CB blog post from NFL was really interesting. They've taken our models, generated new stats, and kind of created a new cornerback rating system. And so it's an article about who's the best quarterback this year so far. And then there's also a fun Instagram link on Sportsball. They did a little segment on what our model is actually doing. If you don't know what Sportsball is, I would highly recommend checking it out. It's very entertaining. Yeah, and then I think with that, we can take any questions you guys might have.